Hello, everybody, and welcome to today's presentation, Best Practices for Containers at the Edge, brought to you by Cisco. I'd like to introduce you to our presenter, Casey Bleeker. He works in the DevNet team, helping to facilitate technology access, content, and experiences to developers around the world. With over a decade of hands-on product programming and customer engagement experience, Casey is well-versed on translating the technical aspects of APIs directly into the real-world value of achieving business outcomes. I'm going to turn things over to you now.
Perfect. Thank you very much. So, as Billy said, my name is Casey Bleeker, and I have been with Cisco for about 5 years now. And previous to joining Cisco, I had about 8 years in various IT industries, predominantly telco-related. I have had many different roles within the Cisco organization. I've been in our sales organization. I've been in our partner organization. I managed a $150 million Spark Innovation Fund, which was for equity and non-equity grants for developers to get involved in our developer community. And most recently, I've joined our DevNet organization. And our DevNet organization is specifically a group that goes around and we help evangelize to all of our customers, as well as just developers in the entire ecosystem, about all the resources and tooling that Cisco has to offer. So these are some of our own events that we host at our customer events like Cisco Live. And but it's not just teaching people how to code. DevNet actually does a lot more than that. We have a lot of other resources. Specifically, we just passed 500,000 members. So we're a pretty large community of developers that are focused on how we can actually leverage the network infrastructure, but also the software and platforms available from Cisco to deliver new outcomes for our businesses. Just a high level of some of the resources that are available to you that you may want to check out after this. We have product portals that explain all the different product portfolios from Cisco in developer terminology, so not just high-level architecture. We have remote labs and sandboxes, so you can actually get hands-on access to a lot of the tools that we talk about and a lot of the hardware that we sell. We have step-by-step guides that we consider learning labs, and these aren't just Cisco technologies. We have everything from how to get started with REST and Coding 101, or getting started with Python or JavaScript, to containers, Kubernetes, service meshes, building cloud-native application architectures. So a lot of learning labs here that are relevant, just not specific to Cisco products, but also just any general knowledge and learning that you may want to have. We have docs and sample code. We have a huge community of community support projects that we host on something that we've just launched called the Code Exchange. So you can actually find a lot of pre-built projects that members of our community have already built to add extensibility to our platforms. We offer forums and support. And then lastly, we actually offer a route to market for our partners, ISVs, and customers. So if you're a developer and you create something interesting that you think other people may want to leverage or use, we actually have a route to market for customers to do that. So that's a very high level of DevNet. And what am I here to talk to you about today? Primarily, we want to talk about edge compute. But before we talk about edge compute, I want to talk a little bit about the IoT industry challenges that have led to edge compute. What are the problems that are being solved by computing at the edge? And why would I really want to compute at the edge? We'll talk about some use cases for computing at the edge. And then we'll talk about how containerization and the different tooling to deploy containers to the edge actually help solve some of those problems better than other platforms may today. We'll talk about the edge compute, which is really being labeled in a lot of different terminologies today. You'll hear it called distributed intelligence or many other kind of semantics being leveraged to talk about really just doing your analytics processing at the edge or at the nearest device to your actual data collection source. We'll dig into containers for edge compute. What are some of the tools that you want to use out there? What are some best practices? And we'll actually do a hands-on here. I'm going to show you guys how we package up a container at Cisco to deploy into our network fabric, and how you can actually use our network architecture as a hosting platform for containers. And then we'll talk a little bit about real-world implementations and talk about how customers are actually using this information today out in the real world. And then we have about 15 minutes carved out for Q&A here at the end. So let's just dive in. So if I'm talking about IoT today, one of the first things that I like to talk to people about is, what does IoT really mean to you? And as I travel around the world talking to a lot of conferences and events, one of the first things I hear somebody say, IoT means a connected thermostat, right? And for most of us, that's probably not what we think of if we're in the industrial space or if we're in enterprise IoT solutions. we probably don't think about a consumer device, right? And we don't think about, if I want to deploy 1,000 of these things out to my customer, I don't want a mobile app that has to go and connect to each one, and I need to have enterprise security and wireless security and manageability of those fleets. So probably not what we think about in the enterprise. Maybe the next thing we think about is the Amazon Echo or some voice-driven assistant. Now, certainly it's labeled as an IoT device, but today, most enterprises are not yet at the point where they want to actually give commands to their IoT devices because they still don't have any visibility into the data from their devices. So this kind of two-way interaction is still not yet fully absorbed or integrated into the industrial IoT space. We might think about some hobbyist boards, Arduinos, Raspberry Pis, Electrons, right? Some different things that we might think of that we can build projects for at home, but that ultimately enterprises or industrial spaces that have $1 million to $10 million cost per unplanned outage hour do not have the ability to run on hobbyist hardware. So they may say, I need redundant network, I need redundant power, GPIO has to be more resilient for the power inputs and outputs. So this is certainly something that we think of for IoT for maybe our personal lives, but certainly in the industrial space or enterprise space, just not quite there yet. And then I think the prototypical thing a lot of us think about industrial IoT is the robotic arm, the giant KUKA orange robotic arm, right? And if you've gone to industrial trade shows, this is kind of where everybody loves to stand and stare. But right now, it's not really an IoT device, right? It's just automated manufacturing. It's been run by PLCs for 30 years. So what does IoT really mean to an enterprise today? Well, I actually Googled on Google Images and I searched for enterprise IoT and business IoT. And I got a bunch of diagrams back that literally look just like internet diagrams. It's things connected to things with lines. Well, that's pretty much what the internet has been for years, right? Since its inception. And so what differentiates IoT from the traditional internet? Well, obviously something differentiates that because we just did a study with Fortune 50 customers all the way down to small, medium business customers, less than 50 employees. And out of thousands of companies surveyed, only 26% of those companies said that they felt that their IoT initiatives to date have been successful. I don't know about you, but if 74% of my work was viewed as not successful by my company, I probably wouldn't be employed very long. So it's very, very important that we think about, well, what are the problems? Why are businesses saying that they don't feel that their IoT initiatives have been successful? One of the biggest reasons that these haven't been successful is because we're not differentiating some of the problems that need to be solved. It's not just connecting things to things, because we've been doing that for a very, very long time. It's actually getting value out of the data from those things. And a lot of times, that's very difficult. In the IoT space today, we've got a huge wide spectrum of protocols. I could pick one of many different transport protocols. I could choose one of many data protocols. I can use different types of services to discover where I want to send data to for an IoT device. I have different data constructs of how I organize and format the data that I'm going to send to that provider. And then I have brokers to actually mediate those connections. And the difficulty comes that I may have one device that picks one set of those constructs or data standards, and I could have an entirely different device that manages or connects through each one of those different protocols. And that leads to this haphazard world where everything is a little bit decentralized, and we need to be able to normalize that data and collect data from hundreds or thousands of different types of formats or aggregations of these transport protocols, data protocols, the constructs, and the brokers those types of devices may use. That's where edge compute really comes in, because it can actually be used to help solve a number of these problems, and we'll dig into some ways in which that happens here in a moment. It's the same thing as once I get to the data aggregation layer, or really the data presentation layer, where I'm trying to get value out of the data. I have one of many infrastructure providers, my own premise or a public cloud provider. I have a lot of different tooling available to be a data warehouse or a data lake. If I'm going to do predictive analytics to try and predict maintenance, or if I just want to do regression analytics to know if something is going to fail in my factory. Artificial intelligence has a huge list of things and architectures and pipelines that I can leverage. I might want to do real-time analytics or real-time dashboarding, and there's a lot of different tools here. So ultimately, these are some of the same problems that we have across the internet today. If somebody's building a web app today, they have to make these same decisions about protocols, about the different data constructs they'll use, about the different message queue or broker systems that they'll use, the infrastructure selections, the data formats, the backend databases, the pipelines. So really, IoT is not that much different than every web app out there today, because we have thousands of these types of selections and choices we have to make along the way. The major difference is that companies are trying to derive value from that data, and IoT exponentially increases the amount and types of data. I think the amount is less important than the types of data. So if we think about this from a very simple format, if I've got a device, the goal of a business is to extract data from that device today. And we want to move that data to the appropriate application or the appropriate destination that is actually going to process that data and give me some outcome that we can then derive business value from. Well, if I exponentially increase the amount of data, it's not as simple as just scaling these things vertically, right? I can't just say more data means more apps means more business value, because these things are actually highly distributed. They are not in this linear format going left to right from data device generator to app that actually derives my business value all the way down to getting actual business value out of those business decisions. Instead, these things are highly distributed, and that leads to a number of challenges. One of the biggest one is that I've got to figure out how to connect and secure and manage these diverse devices. And a lot of data remains locked in sources. A really interesting stat that we just got from that IoT survey that we ran, over 95% of industrial devices are not currently enumerated. And what I mean by that is that they are not actually even being instrumented or monitored. So if we think about the fact that 95% of machines in an industrial space, or CNC machines or sensors that are feeding data to PLCs or through proprietary protocols, 95% of that data is not being captured or monitored. So a lot of the business challenges we have today are basic 1990s BI problems, business intelligence problems of I just want to run reporting of usage of a machine, or I want to just know its uptime, or whether or not it's actually decreasing in speed, or do some very basic predictive analytics on those sources. But that data remains locked inside those devices. And even if we could get that data, we don't know which application to send it to at the right time. Because at one moment, I might need to be sending that data to a data lake to be incremented and constantly stored. But at another moment, I may need to send that data to another application to be processed for different business logic. And we don't have any programmatic way to actually route that data to enforce data ownership, privacy, or security. And that's where edge routing comes in, because this is the problem we have. Our data is sitting inside of our devices, and this is, I like to say that it's holding us hostage. So this little comic kind of illustrates that if I had an IoT connected scale and it said every morning, $50 or I tweet this out, I might be incented to actually do something to get the data out of there, right? And that's what a lot of the businesses that we interact with today have, is they have thousands and millions of data generating devices, but they don't know how to actually extract that data. So from a lot of organizations, and I think this is becoming the IoT industry standard now, or at least understanding, is that some level of distributed intelligence is required. I need something out in this distributed environment that helps me route that data between devices to their designated destinations. And those destinations can change based on the content of that data. So I effectively need some device out there to route the data based on its content, based on business logic, based on business rules. And Cisco said, well, what do we have out here at each one of these nodes that's actually routing already network traffic? Well, we have all of our industrial network devices, and now all of our closet switching line as well, that actually can run business logic and actually run your own applications. So we have reserved processors, memory, RAM embedded in these devices. They already run Linux. Hey, it's not that far of a step for us to start running containers within these applications. So we've gotten big time on board with containerization at the edge and said this distributed network that we already have is a platform for you as a developer to deploy your own distributed intelligence to the edge. So let's dive into distributed intelligence, or edge compute, just a little bit further. But first, we have to talk a little bit about semantics. Unfortunately, this is just the entire business or industry is picking many, many different names for this construct of computing somewhere other than the cloud and other than the data center. And so we would call that edge compute. You'll hear it called distributed intelligence. Maybe one of the more popular ones at Cisco is fog computing, edge fog fabric, data fabric, hybrid compute. These are all terminologies that are the exact same thing. They mean that we are running a compute workload somewhere other than a designated traditional server in a data center or in a public cloud provider. So we talked a little bit about why I might want to compute at the edge in terms of I've got this problem of distributed devices. But let's dig into that a little bit more and talk about why, in very specific technical use cases, I may want to compute at the edge rather than just dumping all my data to some single destination. One of the first ones is that there just may not be enough network bandwidth. A classic use case of this is a oil well out in the deep ocean oil well, and they have on average 150,000 sensors that are sending data at an interval of sub 1/10 a second, so every 100 milliseconds. So if I have millions of data points being generated every second, suddenly I have to figure out, do I filter that data? Do I store that data locally? Do I buffer it? And that really expensive minimal bandwidth satellite uplink that I'm using for operations of that well, it's not exactly the best pipeline to send data to. Now, that's an extreme example, but almost every business has something very similar to that. For instance, if I want to send all my data to a cloud provider, I have to pay for that data ingress and egress, and I have to pay for the storage of that data. And so just reducing the amount of data or the bandwidth that is needed to send that data to some destination, even if my ultimate destination is a public cloud provider, putting a device at the edge that can aggregate, compress, and filter that data dramatically reduces the data that I need to send to that destination. So lots of use cases for that in the enterprise, and one of the biggest right now is just cost reduction of public cloud provider costs. Most of the data that an enterprise sees in an IoT world is just not that interesting. If we take the use case of a IoT-connected fire alarm, they oftentimes are set by default to send a no fire or all clear signal on a regular interval. Well, that's not very interesting data because I see a fire alarm and it just says no fire, no fire, no fire, no fire. Well, if I have thousands of those across a campus, I don't want to pay money to have that data sent to a cloud provider or sent to my own data center and then stored in a data lake or stored in a database. I just want to filter that data at the edge. But when that data becomes interesting, suddenly I want to do something with it. And this is what's very interesting is that most IoT data is most valuable the closer you get to the time of its generation. What do I mean by that? I mean that when data is generated, it has the best business value to actually give some outcome, whether it's deriving a business value decision based on artificial intelligence or machine learning or long-tail curve analysis. But your data scientists or the analysis that you want to do with that data is most valuable closer to the time or point that that data was generated. And we oftentimes summarize this as latency optimization. There are lots of use cases, for instance, an IoT edge device sitting in a connected autonomous car. Well, if it is doing some machine learning algorithm to say, should I detect a pedestrian and brake? Well, you probably don't want to have the delay of sending that round trip to a data center, to a cellular provider, to a public cloud provider. A lot of that optimization or that calculation or computation has to be done at the edge. And that actually applies to a lot of security use cases for building facilities in IoT spaces. For image analytics in cameras, we're seeing a lot of video cameras starting to do the image analytics in the camera itself because of the latency, that they can actually process that on-prem or in the device a lot faster. And then especially in manufacturing. If I have thousands of sensors across a conveyor belt of devices that are being manufactured and they're all doing quality control, if my device has to pause at every single one of those, suddenly my manufacturing speed dramatically slows, and I'm constantly waiting for this latency return. And if I'm not waiting for that latency return and I'm doing quality control on a device, I might kick off the wrong product if I detect that one is wrong as well. So the use of data is often at the edge, and that's where latency optimization comes in. As you start digging into data science, and this is something that I encourage everybody who's in IoT today, is to take some basic AI/ML or data science courses, because really what our job is in IoT is to get data to a data scientist. And if they don't understand, if we can't speak their language and they can't speak our language, we can't help solve problems together. And one of the biggest use cases for edge compute is partitioning of data, of actually chunking and munging data so that it's in an optimized format to be computed at ingress in a data lake or a data warehouse. And this ultimately means just changing or formatting or chunking data to go into the right destination so that when it's pulled in real time, the compute operations in the central location, either a public cloud or in your data center, can handle hundreds of millions of those types of devices simultaneously at a lower compute threshold. And segregating out those operations out to the edge drastically reduces the amount of compute that's needed in a central location. The other use for this partitioning of data or chunking data to different destinations is security. We see a lot of organizations today that are starting to back away from the mistake they maybe made of just throwing all the data into a data lake, setting no role-based access control because they don't know what's in that data lake, and then just saying, oh, well, we didn't realize somebody could actually correlate these data points or correlate these types of items. So from a security perspective, actually doing role-based access control based on where you route that data is very important. Data normalization, very similar to kind of chunking or partitioning that data, but in that first slide that we talked about all the different protocols and the different brokers, we can actually interoperate those brokers or that data formatting at the edge so that every application upstream from that can expect a consistent, simplified data format. And that means you can choose your organization's canonical data format and normalize all the data that you're ingesting at the edge into that format. And when you choose to change in incremental pieces of your architecture going upstream, you don't have to code or customize to support thousands of different formats. You can choose to normalize upon one data format. It's very, very important going forward as these IoT environments become more complex. Hardware interfacing. Hardware interfacing is probably one of the biggest use cases for edge compute, primarily because as I start to look at edge compute today, as I mentioned, 95% of these devices are not IP enabled out there today. In the industrial space especially, we see lots of legacy protocols like Profinet, Modbus, SCADA, all the legacy controls there, and I need some serial hardware interface oftentimes to interface to that physical device. And then data redirection based on the content of the data. This is really exciting as a traditional network guy. You know, if I start to think about the fact that I can have an application, a containerized application that is inspecting the data, sitting on a router at the edge of the network, and based on the content of the data, route it to different destinations, that is effectively a layer 7 router at real time. And so we can actually say, take the example of a fire alarm. When the data says no fire, no fire, no fire, I can actually send that data maybe to a bucket where it just gets dropped, right? But if it says, hey, low battery, and now I need to replace that, I can actually send that to my facilities crew. And I can send that to a different alerting system altogether to aggregate and find out the information about my batteries or the life of my actual fire alarms. But when it actually says fire, I probably don't want to go alert facilities or my maintenance crew or my IT team. I probably want to actually go alert emergency facilities to respond to that fire. So the data direction and content of that data can all happen at the edge. And if every edge device is processing that, I don't have some massive workload in my data center or in a public cloud that I have to send all that data to manage all those rules. Lastly, as I mentioned, data analytics is very important as we start getting into the space of aggregating data at the edge. One of the big use cases is actually time stamping. We've had enterprise data scientists let us know that they have had trends in their manufacturing facilities that they would not have been able to detect if their timestamps were not accurate within milliseconds. And so if I think about the fact that I've got dynamic delays, and oftentimes in today's public cloud environment, timestamps are added to data at the moment that they're written to databases, suddenly the timestamps of my data could be off. And if I've got thousands of embedded devices that don't have the ability to have synchronized clocks or synchronized network signals, now I don't really have a method to actually stamp those data points even at the device themselves. So one of the big use cases is actually ingressing this data at the edge where there's extremely low latency, putting a timestamp meta tag on top of that data object, and then sending it to a database where it's written with that original timestamp. And this allows a lot of use cases for correlation of events and predictive analytics. And then lastly, one I think that we should all be aware of is algorithmic ownership. As we start getting into this data-driven world, data is the core intellectual property of a business. It is the most valuable key. And the more data you can get, the more valuable your business is going to be because you're going to be able to have more visibility into the outcomes you can deliver for your customers. And the key phrase out there today is feed the beast. Just give it as much data as possible to get all these types of outcomes. Well, if core IP for my business is maybe retail oriented, I may not want to share that data with a public cloud provider algorithm that may enhance itself off of those data points. And so you have to start thinking about, when I feed data to something, I'm not just getting the result, but I'm also sharing the insights with that third party. And a lot of organizations today say, I need to be able to do that in-house. I have to protect that core intellectual property of my business, which is my data. And I can't share the insights into that data with other competitors. So ultimately, I need to be able to own that algorithm and own the ownership of the data and the insights that get made by viewing that data. So obviously, lots of use cases for computing at the edge. How would one traditionally deploy an IoT edge architecture? Well, today, if I'm thinking about maybe a traditional public cloud provider, I would have to provision some form of gateway. And this is the destination my device is going to send its data to. And I can either provision that on-prem on a piece of physical hardware or in the cloud. And there's an app that sits inside this gateway. And you would, as a developer, write that app to receive the data, process your business logic, do all the different rules we talked about just a moment ago. And all that logic sits inside of this application. But now I actually need to go and provision that IoT device to send its data to this gateway. And oftentimes that's not as simple as I think, because now I may need to actually install an SDK on that device. I may need to have a physically connected device to its physical interfaces and write an app to read that physical interface and then send its data to those destinations. And then I need to register that app or the SDK on the device into my gateway. And then now I start sending my data to that gateway or that application. And now I need some other logic in the actual edge gateway or cloud gateway to say, now where do I make the destination? Where do I send that data? So maybe I want to send it back on premise. Maybe I want to send it to a public cloud provider. And wherever I send that data to, I now need another application to write to receive that data. I have to actually have some sort of a service or managed environment to receive that data and start processing it based on the data that I'm receiving. And now I need to implement policies in either my cloud or premise environment of where am I going to share that data to? Is it going to go to third-party tooling for predictive maintenance, machine analytics, new service creation, right? Or customer environment data? And that could be either on-prem or in the cloud. And if I look at this architecture, I start going, man, that is a lot of coding and deployment of apps, right? A lot of solutions out there today try and make some of those out of the box fit your business, but ultimately you still have a lot of logic layers to write and deploy. So from Cisco's perspective, we said, let's see if we can make this a little bit simpler. So we have these industrial devices that sit out in the edge of a network. They provide basic network connectivity to environments and to industrial environments, from everything from transportation buses down to industrial manufacturing plants and oil and gas. And when we bring one of these online, it actually registers itself automatically, either over cellular or over your traditional wireless network or wired network, to our Cisco Kinetic Gateway platform. And then it provisions itself and says, here's your policies. And your policies include an application. And this gets deployed down from our cloud. And this application could be any from Cisco or a third party, or one that you build yourself, which we'll show here in just a moment. We then have a library of southbound device connectors. And these device connectors are built to integrate to all those thousands of different either proprietary protocols or physical hardware interfaces. And they automatically connect those devices into our gateway, into a format that your application can now automatically read. And so now you have written one application that lives at the edge of the network, which does the data processing, which does the business analysis and route gathering, and applies the policy to that data. And now you can choose where you would send that data to whatever platform as a service or cloud provider you would like to do, to send that predictive maintenance or do machine analytics or any new service creation that your business would like. So let's just show that in practice here real fast. So let me get my screen over here. So I have, I've got a little file folder here, and I'm just going to open this up in my code editor, and let's just see what's all in here. So what I have right now is I have a little Docker file, and this is what we're going to package up as our application that's going to run at the edge of our network. So if you're not familiar with Docker files, we definitely have some 101 getting started guides with Docker all the way into Kubernetes and service meshes. And so this is as simple as it gets. We are basically going to choose an Alpine, the Alpine latest image. We're going to give it a label, and then we're going to give it just one run command. And this is actually, we're not even installed, we're just using the native Alpine package manager to install something called Mosquito. And Mosquito is an MQTT broker, because one of the applications that I may actually want to run at the edge, while I could run Cisco's broker platform or others, I may want to just run a Mosquito broker to actually aggregate and normalize that data and queue it at the edge of my network. So we're going to run to install that, and then we're going to clean up some of our temporary files just to make our container image a little lighter. And then I'm going to expose the network port that Mosquito broker is listening on. And then every time this container starts, it's going to run this entry point command. Okay? So from a very high level, we have basically written an application, even though it's not really an application. We're putting together a container file that is going to run a very basic Mosquito application. And it's going to run an MQTT broker at the edge of our network. So let's take a look at that. So if I run right now, if I go over to its command terminal and I try and connect to my local host with a Mosquito or MQTT command line, I see that I get connection refused because it's not running right now. Okay. So now let's just go ahead and let's just get this thing running. I am going to just run my Docker build file. So I'm going to say Docker build, and then I'm going to give it a tag. And my tag is just some organization and then the name. And we can see here, this was built from cache, but it actually happens about that fast, quickly, normally as well. We took our base image, we gave it a label, we installed Mosquito inside of that container, we exposed the network on that Docker container, and then we set the entry point. So I now have this Docker container image built, and I can run this container image locally on my machine. Let's go ahead and do that right now. I'm going to say Docker run. I'm going to open up the port 1883, and I'm going to map that to the port 1883 on that container. And then I'm going to run this in interactive mode, which means I can easily exit out of it and watch the logs here. So I can see that as soon as I run this container, it launches Mosquito, and I can see the command prompt or command logs output from that Mosquito broker. So I'm going to come over to a command line here. Now we can actually sub to that, and I don't get the connection refused because now my container is actually listening. And when I start publishing, you'll see when I publish data to my broker, it's being pushed back to any connected clients. So I now have a MQTT broker running on my local machine in a container. Let's move that container into a format that can be deployed out to the edge of a network. And this could be any complex application. This could be a Python application. This could be your Node.js application. Any containerized application can follow this same process. This is probably just about as simple as it gets for IoT. So I'm going to exit this file here. And let's go back and take a look at one other folder file that I've got here. So we have a Docker file, and this is following industry standard formats for how to compose a Docker container file. But we have one other package file that we call package.yaml, and this actually gives us a little bit more information about how much resources do I want to allocate to this container when I push it out to my network. What physical ports on that network device do I want this to have access to? Because even the application ports that this container, when it gets pushed out to the edge of our network, when it gets pushed out there, it's going to have these little this connection inside the router that I can set all the same network policy I would as a physical network port. So I can set a VPN port on this device. I can actually set firewall policies going into this container. So we set that interface name here, and we specify which ports it's going to open. And then what we do is just one simple command line. We have this tool called IOX client, and this is a simple CLI tool that you can download from Cisco that basically takes that Docker image, and that happens in just a moment. And you'll see here now we have this package.tar.gz. So what we've done is we've taken the layer images, and we'll talk a little bit more about layers here in a moment. We've taken the layers of this composed Docker container, and we've packaged them up into this zipped tar file. And the zipped tar file is exactly what we're going to push out to the edge of our network. Okay? So let's go ahead and show that real fast. So this is actually Cisco Kinetic. This is our cloud-based management platform, and I can see here that I've actually got a gateway sitting out in San Jose, and I can see that I can see its GPS history, I can see its current address, I can see the current health of that device. And if I go into my gateways here, I can actually drill in there and do some more information. I can do debugging analytics. I could actually VPN into this device so that any device downstream I could administer as a manager of an IoT environment. Right now, this one's not cellularly connected. It's actually just connected over a wired connection. But I can do all kinds of diagnostics here. But one of the things that I can see here is apps. These are the applications that are running on that gateway. And you can see it says none. Right? So I have no applications right now. So let's load an application onto that device. So if I go to Fog Applications, these are the actual container, packaged container applications that we have done the process we just did, building a Docker image, compressing it with that IOX client application, and now I can just click this Add Application button, select my app package, and now I'm going to be able to go right to, let's find it here, Mosquito Broker, package.tar.gz. Now, I'm not going to import this one right now because it's actually already imported and it's going to give me an error because it takes about 2 minutes to import. So just so you guys don't have to sit and watch that import process, it will upload that file. Now, by the way, let's take a look at how small that file is. This is pretty cool. If I look at how small that is, I'm looking at the 2.1 meg. So a Mosquito Broker in the Linux container file system is packaged into a 2.1 meg file. So pretty small. And that's something we'll talk about here in a second for best practices. So we can keep these nice and light. Once I've uploaded that file here, so that's this IOX Docker Mosquito Broker here, I can now say install, and I can go out and choose which gateway I want to install it to. I can say, let's push this out to every gateway, or let's create a policy. And here I can actually override the amount of compute that I want to give to that device. So maybe I want to give it a full 1.2 gig CPU with full cores and then 512 megabytes of RAM. And then I can choose which gateways I want that to be deployed on. And that's going to override those default settings that we had before. Here I can actually override those network settings. And then I can actually just click install. And that's going to start installing that application out to the edge of that device. And that just takes just a couple minutes. So hopefully that shows you that we can take Docker industry standard containers, we can package them up in a very easy to use way. By the way, there's APIs for all the devices to manage this if you don't want to do this through the UI. So you can actually tie this into your CI/CD deployment pipeline and say, when I deploy new applications, we're going to bundle them up, we're going to package them, we're going to send them out to the edge of our network. So let's dig in a little bit more about best practices for containerization. Obviously, we use the Docker client build. We also support native LXC container images as well. So it does not have to be a Docker image. In fact, that's what our IOX client does, is it converts the Docker native image library into a LXC style image. So you can use either Docker or native LXC. You can pull directly from public registries into those images. And then you can use the IOX toolchain. So you pull in your Docker image, you create that Docker image. We use that package.yaml file to define the resources that would be available to that device. We use the IOX client to package that up, and then we get this tar file, which is our compatible app that can be pushed down. Now, if you've been in containers for long, you may have heard of this analogy of cattle versus pets. Cattle versus pets meaning that if I think back as an IT administrator years ago and I had a VM that ran my email system, that thing was a pet. I cared for it. I fed it. If the CEO called me and said they couldn't get their email, I went and checked on that thing. Well, I took it to the vet, right? That was a pet. Whereas if I have an application that is microserviced and running in containers, if one of those containers doesn't behave well or is getting sick, I just replace it with another. Now, it doesn't like that analogy, but that's something that a lot of people have been talking about is cattle versus pets. Well, if I think about containers at the edge of my network, I can't think of them like containers, like cattle, because this isn't a public cloud instance. This isn't something where I have infinite amount of compute. I need to think about the fact that I probably need a shepherd dog or a cattle dog for my cattle, right? So it's still something that I want to think about as I have this mass herd of containers, but I need something to actually shepherd that flock of cattle, that herd of cattle. So the first thing is we need to implement resiliency and health checks in all of our containerized applications. So adding 200 OKs, add a health check endpoint, and giving that health check endpoint back to our container platform will help dramatically increase the time that it takes to restart your containerization process if something goes wrong inside that container. Just briefly, we've seen that most containerized enterprise applications today do not implement health checks appropriately. So definitely you want to think about adding your health endpoint that responds and gives a 200 OK when your application is alive. Load balancing, right? I may want to think about the fact that load balancing may want to be an external process. A lot of people today will spin up a separate sidecar container, maybe like Nginx or Envoy, and those are great for public cloud environments. But if I have limited resources, I may want to have a physical load balancer, or I may want to designate a containerized application to load balance my traffic. We also need to have some consideration about local protocol interfaces. If I have a container bound to a physical serial device, that serial device is not a multi-duplex connection, meaning I can only bind that serial interface to one application at a time, which means that the container that is containerized application that is bound to that serial interface needs to be resilient. And I need to plan for, if it has an application problem, I need to be able to unbind that serial protocol interface or that local physical hardware interface, and I need to release that back so another application can bind to it. Redundancy of physical devices, right? If I have some mission critical enterprise data that I need to be aggregating and collecting on a regular basis, I need to think about the fact that at the edge, as I'm making these applications, as I'm making this application logic and processing the data with all these different rules, I need to add some redundancy of those devices. Some basics as I start to think about building container images for the edge is we need to definitely think about limiting resource consumption. We have a lot of new resources coming out in terms of edge TPU or edge machine learning. We have a lot of resources coming out from Cisco where we have a lot of reserved compute, but we still need to be thinking about limiting the resource consumption as much as possible. Starting with lightweight images like Alpine, Yocto, Scratch, that can help a lot, okay? I definitely recommend, and it's not the Scratch image, it'd be building your own Scratch image. We still need to actually implement security and process control with C groups. So natively, Docker does not actually limit the process restraints within each container. You need to be able to go in and set your own C groups policy controls in the container itself. So as you build that Docker file, you can set some policy controls on each resource to limit resource consumption within the container itself. Across almost every enterprise platform today, we allow no privileged host permissions. Nowhere in Cisco can you run a container on any Cisco platform with a -- privileged command. So as you start to debug your application or build out your application, if you're relying on certain things to bypass properly set C groups or to bypass resource constraints or to map network protocols in a way that isn't standard outside of your container environment, and you're using the privileged host permissions, you're going to have solve that in its root problem, because we do not want to allow any container from one vendor and another to talk or affect one another. So no containers are ever allowed to run in a privileged host permission mode. And then just some best practices that as you get into containerization, you don't want to forget about. You want to limit and combine those layers. As we dove into that container file, every one of these steps in that Docker file builds its own layer. So every one of these commands builds its own layer. And so here you'll notice I do this and the tag at the end. This is combining this step into one full layer, and each layer takes up a substantial amount of space in that environment. So limit the number of layers that you need in your files. Also plan your layers for deployment. Our IoT infrastructure and many others today support this idea of multi-layer distribution deployment models. So for instance, if I had two applications I wanted to push to this edge device, one was already there. I built it on the Alpine image. I'm using Python to run that application. So I pushed the Python SDK and the Python engine down into the Alpine image. And then I have my own application that's running on that. If I want to go now push a Node application using the same base image, it's going to just have to install the Node runtime and then the Node application, but it's going to reuse the Alpine layer. And since that's probably the biggest layer of my application, I'm really just pushing down a very small amount of code in those changes. So layer reuse actually helps conserve the resources at the edge in a device, but it also increases the speed for deployment. So with that, I think we're coming up on Q&A time here. I want to leave you guys with just a few more resources. In this deck, there are a lot of slides on real-world implementations, including a video where we've actually implemented this type of deployment with the city of Braga in Portugal. They deployed these industrial routers across their buses, and they actually do some CDN caching at the edge for their mobile users, but they're also aggregating the physical GPS data and engine health data from the bus to do predictive maintenance, as well as predict where and when that bus is going to arrive on time for its next stop. But if you want to dig into this, we've got a lot of resources that you can dig into here as well, and there's links in the PDF that you guys will receive after this presentation. Kinetic Learning Labs, we have step-by-step guides to go through the whole cloud platform that we just walked through if you're interested in learning in that. We have a sandbox environment where you can actually deploy your own applications to edge routers, where you can actually write your own applications or deploy our own edge logic to do a lot of the logic control that we've talked about. And then IOX Learning Labs, packaging up a container to be able to run anywhere in the Cisco network platform. And then if you're just getting started and you want to know more about basics in Docker, we have Docker 101 Learning Labs, Coding 101 Learning Labs there as well. So definitely take a look at those. And with that, I'm going to turn it into Q&A and see if you guys have any questions.
Awesome. Our first question is Mosquito Broker TR50 compliant?
That is a good question. I don't know. The thing we'd have to look at is, so Mosquito itself is an open source implementation of MQTT. I believe that there is a variant of the MQTT protocol that is compliant, but I don't know if the Mosquito implementation is itself. So that's something that we need to look into. Oh, and on that same topic. Real quick. One add-on to that as well is PAHO MQTT is probably, and they're backed by Sun, is probably the biggest library that you would want to probably start to implement and use. Mosquito as itself is just a quick and easy to use command line tool, but also does have some decent quality brokers. But PAHO is probably something that I would imagine if there is a compliant broker out there, it would be from PAHO.
Great. Our next question is, instead of cloud management, can we do local management?
You absolutely can. So I didn't show that here. I could actually have pushed that package to an edge router via command line. We also have a GUI tool called Fog Director, and then there's also a local web interface on every router that supports these. So you have 3 local management ways. You have one tool that can manage your entire fleet or edge compute device called Fog Director. You install that on a local server, and it manages all your edge devices. You could CLI push that package to a local single device one-off, or you could actually browse to a web interface on that edge router and upload that package directly into that device as well. And that is actually probably the most common use case, is actually not cloud managing those devices. They do not need to be cloud managed to get the same use cases and outcomes.
Awesome. Our next question is, where can I get started with these tools?
Yeah, so I definitely encourage everybody to check out developer.cisco.com. In the PDF that you guys are going to get sent out, I put links on all those different resources. And I think the biggest thing there is if you're just getting started in the space, we have a learning lab for IoT standards and protocols that walks you through the details of MQTT, the details of WebSockets, the details of some of these kind of simultaneous duplex protocols, as well as a lot of the transport protocols that are kind of out there today that we support on our hardware endpoints. And then as you want to get into the software development side, we've got open source tooling for, hey, how do I start building my own Prometheus or Grafana or Elk Stack for real-time data analytics? We have our own products we sell, but honestly, most developers want to write that stuff from scratch, and sometimes it's even faster, right? So we have a lot of tooling out there, and we're big supporters of the open source community in those spaces. And then we also have Docker 101, Coding 101, Python 101, JavaScript 101 labs. So if you just want to get started and you're just getting IoT, one of the things that we always see right now is we have 2 diverse audiences. We have IT folks that want to get into IoT, and they don't know anything about the original OT landscape and world. And they need to learn about that stuff because there's stuff that's very important to the business, like uptime and resiliency and security, and those concerns they need to understand. And then there's the opposite side. We've got the OT team who's trying to understand some IT concepts, like how will I actually securely put this onto the network, and how has the network team been segregating traffic securely for decades, and how can that actually be implemented into my industrial space. So I definitely encourage, I think it's going to be a fun time as these IT and OT groups merge into this IoT organization structure.
Great. Our next question is, what is the biggest use case you see today for edge compute?
So I think the biggest use case I see today for edge compute is hardware interfacing. Right now, we're still in this kind of transitionary period for the next few years where most organizations don't even have visibility into their data, let alone do most OT groups want to actually allow you to send commands or downstream commands to their industrial spaces or to their sensors or to their automation control systems. So right now, a lot of organizations just say, I just want you to suck up that data, and I'm not planning on replacing the interface to my $20 million CNC router. I just want the data off of it, right? And so physical hardware interfacing is huge, and that also helps with legacy protocol interpolation and normalization. And if I think about like half the models of CNC machines that are in use out there today that cost hundreds of $1,000s a runtime hour, they're dumping their logs on an FTP file server that's stuck on an embedded little device. So how do I get that data off? How do I get that data off in real time? And a lot of times that's physical hardware interfacing and then that legacy protocol normalization to something that I might expect to use up the stack, like MQTT with JSON or a standardized canonical format, and normalizing that data up the stack so that I'm not trying to parse, legacy FTP files or Modbus or SCADA protocols data signals in the cloud or in my central data center.
Great. Our next question is, how much logic/intelligence do you see in IoT sensors?
That's a good point. So I think right now we're getting into, we've got all the system on a chips, we've got embedded CPU processors. I think a lot of this logic can get moved out to those edge devices and will. I think we have to think about, what is my use case? If I wanted to start my own Nest thermostat company, this is probably not an architecture. I don't want to ship a Cisco router or an industrial device with every consumer device, right? I think we have to marry those lines, or at least define them and say that there's some use cases where devices are going to be consumer facing or consumer focused, and those will need some local processing, some local compute. And then in the industrial space, there's a lot of use cases for doing edge AI ML or edge analytics. And there's these data processing, the concepts and the business outcomes can absolutely consume a huge amount of compute and resource at the edge. The question is what's the replacement cycle? We've got a lot of legacy hardware and a lot of legacy controllers in industrial and IoT spaces. And I think as new devices, if I'm implementing something new, I can expect it to have some compute workload and the ability to maybe run a third-party SDK. But a majority of the world today is on a 20 or 30-year refresh cycle for some of this hardware and equipment. And we're going to see that kind of trend slowly taking place, I think, over the next 5 to 10 years. But absolutely, I see a huge amount of increase of compute being distributed out to the edge.
Our next question is, what about Kubernetes? Do you see this as a valuable tool for the edge?
Yeah, so actually Cisco just entered into a partnership with Google, and we were the first Google Kubernetes Engine certified provider. And so Kubernetes is a really cool tool to say, when I deploy thousands of containers in my data center, how do I manage them at scale? How do I give tools to developers to integrate that into their development pipeline? And we have gone all in on Kubernetes at Cisco because we have something called the Cisco Container Platform that runs in our data center. And so now we have Kubernetes environments in the data center that can marry with your public cloud provider. So your developers can have this seamless experience of deploying applications to the data center as well as to the cloud. And I think in the next 12 to 24 months, you're going to see a huge adoption of Kubernetes at the edge as well. Because if I just wrap that container that we just built in a Kubernetes command cluster, now it can be managed and controlled with all the other logic and infrastructure. And frankly, a lot of customers say, why would I want to use this Cisco management tool? Sure, we'll use your tool to deploy the application, but to manage it, to monitor it, to actually scale it, to deploy it in different workloads, or to refresh or upgrade that application cycle. The best open source tooling is available out there for free today in Kubernetes, and that allows your development teams to kind of follow the open source best practices, so that if 3 years from now that's no longer the best tool, you can replace that and put the next open source stack in that environment. So that's very much where we're going at Cisco, is to follow the developers' lead and follow where the open source community is driving the industry, and saying those open source tools you can run natively in our data center without needing to have any proprietary Cisco involvement in that. I think we're going to see that data center expansion of Kubernetes out to the edge over the next few years.
Great. The next question we have is, what are your thoughts on AI/ML at the edge? Any suggested platforms to explore today?
Let's see. So if we just talked about Kubernetes out at the edge, right? And so Kubernetes is going to help manage our containerization platform, but right now there's a challenge of hardware interfacing, right? If I want to do AI/ML at the edge, I need to actually have physical hardware access. And if you've ever tried to do AI/ML with GPU access in a Docker container on a Mac or a Linux machine or a PC, you know that there's a lot of hardware constraints in very specific environments. So I think you're going to need to have hardware validated designs for AI/ML at the edge. We're seeing that with Google's Edge TPU, but right now there's no containerization support, so I'd have to go manage that as a Linux box at the edge, which is basically then just an industrial PC, and that's very difficult to manage. And a lot of industrial PCs don't have that kind of, industrial rating that's required. What I see as very exciting or powerful is that right now there's a lot of work to take that Kubernetes engine and give it hardware support. And Kubernetes has a huge involvement or huge community behind it in something called Kubeflow, Kubeflow, and Cisco's a big supporter of that area as well. Kubeflow allows an AI/ML developer to deploy onto their developer stack without being a developer. So they can actually deploy their AI/ML pipeline into a Kubernetes cluster. So what we've done is we've given the tools to the IT team to build Kubernetes clusters without having to know how to do that. Now the developers have access to Kubernetes tooling to deploy their applications the way they are used to, and they don't have to talk to the IT team about all the nuanced details. And then the developer team can say to the AI/ML team, hey, let's build you a Kubernetes cluster and manage and give that to you. And now the AI/ML data scientists can deploy their pipelines without having to know anything about Kubernetes. So we're abstracting all these components out, and IT gets to manage the infrastructure, the deployment, the security, the network, the uptime. Developers get to manage the developer experience, the developer tooling, and the stack that they're used to. And then the AI/ML data scientists get to deploy their data pipeline on that tooling. You can imagine that's already happening in the data center now. You can imagine that as Kubernetes becomes prevalent at the edge, Kubeflow and other AI/ML tools to deploy machine learning pipelines at the edge will become very valuable. And I think in AI/ML or in IoT, that's the most valuable, because now I could actually take data at the edge, see if it matches an algorithm or an AI/ML trained model. And if it doesn't, I could have been buffering the data for the last, say, 5-10 minutes. And I can send that data now up the stack to maybe my data center or my public cloud provider, where I take this new data and I go retrain the model. So if data is not matching my trained model or algorithm, I'm going to be able to aggregate that up. And guess what? We've got Kubernetes to deploy my edge logic. So once I have a new model, I can automatically redeploy that back out to the edge. I think that's the vision we're all headed towards right now, is this full CI/CD DevOps pipeline to manage logic at the edge. And I think that Kubernetes and Kubeflow will kind of help integrate both developer workloads as well as AI/ML workloads with Kubeflow.
Awesome. That looks like all the time we have for questions. Is there anything you would like to add before I close things off?
I think that's it. Thank you, everybody, for hanging out with me today, and hope everybody has a great week.
Awesome. Thank you. I'd like to thank you, Casey, for a great presentation today. I'd also like to thank today's sponsor, Cisco, for providing the DZone audience with a great webinar presentation. And lastly, thank you to the audience. We hope you learned something new today that will help you in your developer career. Have a good day.